I'm Dr. Matthew Daws. I'm a lecturer in pure mathematics at the University of Leeds. My research interest is in functional analysis, which deals with matrices, typically infinite dimensional matrices. Today I'm going to talk about finite dimensional matrices, but many of the ideas are the same. So what is a matrix? A matrix is just a collection of numbers. There's a very simple matrix. We can think about matrices as encoding simultaneous equations. When we're thinking about eigenvectors and eigenvalues, I think thinking about matrices as geometrical objects is better. So today, what's important about a matrix is that you can multiply vectors by matrices. So if we multiply this vector by a matrix xy, it's very simple what happens. We simply get x, 2 lots of y. Let's think about why that's true. So we multiply across by down and across by down. So the x direction stays exactly the same. The y direction gets scaled by 2. If we think about this on a set of axes, then I like to think about this by drawing a unit square and thinking about what happens to it under the transformation. Here, the x-axis stays the same. The y-axis gets scaled by 2. So the new square is twice as tall. That's all very simple, and that's because this matrix is diagonal. To deal with more complicated matrices, we'll find that eigenvalues and eigenvectors often allow us to reduce to this very simple situation. Okay, so let's think about a more complicated matrix which isn't diagonal anymore. So 2.5, 1, minus 3/4, a half. Let's call this matrix M. So in your A-level syllabus, you will have often calculated the invariant points for a matrix. So let's do that in this case. So I'm interested in solving the vector equation mx equals x. Let's substitute this in. So we're hoping that this is going to be equal to xy. Let's calculate what it is. It's 2.5x plus y minus 3/4 x plus a half y. And then we're hoping that that will be equal to x, y. So that's the same as 1.5x plus y equals 0 from the top row, and from the bottom row, we get minus 3/4 x minus a half y equals 0. Okay, so let's consider a more complicated matrix now. M is 2.5, 1, minus 3/4, 1/2. So my point of view in this lecture is geometrical, so let's think about this geometrically. It's easiest to see this on a diagram. So on the left-hand side of the screen, we see a unit square drawn. The red direction is a unit in the x direction, and in green, I've drawn a unit in the y direction. Now the matrix M transforms this onto the right-hand side of the screen. So the x-axis, the unit vector in the x direction has moved to 2.5 minus 3/4, and the unit direction in the y has moved to 1/2. And the grey square has moved to this parallelogram object. Now, it's rather hard to understand as it is. However, once we understand what happens to a unit square, we understand everything, because we can always move any vector as some combination of moving in the x direction and some combination of moving in the y direction. Consequently, this grid gets transformed to this sort of twisted grid by the matrix. Let's perform some analysis of this matrix, which will help us understand the transformation better. Something you do in your A-level syllabus is to calculate invariant points. So let's do this first. So I want to solve the matrix equation mx equals x. So let's substitute this in. So I want to multiply the matrix by an arbitrary vector. This will give me 2.5x plus y minus 3/4 x plus 1/2 y And we're hoping that this is equal to exactly the same vector. So this gives me two simultaneous equations. 2.5x plus y equals x, minus 3/4 x plus 1/2 y equals y. I'm now going to subtract x over, so I get 0, and subtract y over, so I get 0. So my simplified equations are now 1.5x plus y equals 0, minus 3/4 x minus 1/2 y equals 0. But these are actually the same equation in disguise. They both say that y is equal to minus 3/2x. So the invariant points for the matrix M are all of the form x minus 3/2x. So we have an entire straight line of invariant points. We always expect that because once we have one invariant point, we're completely free to scale it. And because the matrix commutes with the scaling operation, we'll still have an invariant point. I now want to pull a rabbit out of the hat and just consider a vector xy, which is going to be t, times the vector 2 minus 1. We'll see in a moment a more systematic way which would have allowed me to calculate this vector instead of just guessing it. Let's multiply my matrix by this vector. So I get 2.5, 1, minus 3/4, 1/2, times my vector xy. So the t, I can move out the front. So I get the matrix times the vector 2 minus 1. If I then calculate that, I still have my t. I have 2.5 times 2, which is 5, minus 1 times 1, minus 3/4 times 2, that's minus 3/2, plus 1/2 times minus 1, it's the same as minus 1/2. Then, simplifying that, I have 4 minus 2. What's interesting is that is actually twice 2 minus 1, which means I get twice the vector I started with. So any vector of this form, again this forms a straight line. If I start with this vector and I apply the matrix to it, I simply get twice the vector I started with. Again, we can draw this on a diagram. So here I have marked, so no longer am I using the axes, I'm now going to use the two vectors I just calculated. So in red is the vector 2 minus 3, which is invariant, and in green is the vector 2 minus 1, which gets scaled by 2 by the transformation. So with respect to these two lines, it's very easy to see what the matrix is doing. The red vector remains fixed, and the green vector simply gets doubled in length. So I'm going to show you an animation here. Again, on the left, we have my original space, and on the right, we have what the matrix does. In grey, we have the original set of axes. In black, I've chosen a new set of axes using the vectors that we've calculated. So the new x-axis is going to be in the direction of the green vector, and the new y-axis is going to be in the direction of the red vector. So the animation is showing you what happens when we move from one set of axes to the new set of axes. So once we've moved from the old set of axes to the new set of axes, we have actually exactly the same picture as I started this talk with. So with respect to the new axes, nothing is happening in the x direction, and in the y direction, everything is simply being scaled by 2. So if we're willing to live with having to choose a new set of axes, we can understand the transformation very, very easily because all it's doing is scaling the y direction by 2.